Is my screen okay?
Yep, that looks good.
We're just gonna wait a couple more minutes to see if other people are gonna join. Can you hear me okay?
Yeah, you sound perfect.
Okay, cool. How many people are in the meeting?
There's 6.
Okay.
Olivia, this is Ken. Can you hear me now?
Yeah, I can hear you now.
Okay, I have trouble with the microphone, so I may lose you. Is there a phone number I can call if I lose the audio?
Yes. 514-220-2594.
Great, thank you.
Perfect. So it's 8. Admit. Oh, I think Anne had problems with.
There it is.
Okay, perfect. Hi, Anne.
Right, so it looks like we have everyone here except for Rob, Paul, and Ali.
Ali should be here.
Yeah. We could start though.
Okay. So hello. My name is Olivia. It's nice to see you, not just through email. I'm the team lead, so I'm gonna be presenting a bit our slideshow. Our slideshow is a bit long, so we're gonna go. So if you have any questions, just interrupt us, and we'll just go over the rocket as you see fit. So this is an overview of the CR-24 Lazarus. So we're participating in the 30,000 feet COTS with a solid propulsion motor, the N5800. So here's just a short overview of what we're going to see. Again, it's a bit long, so if ever you think it's too much or it's complete, we can move on at your pace. So I just want to present our team leads. So as I said, my name is Olivia. I'm the project manager and the recovery lead. We also have Pierce here, who is our senior chief technical officer. Then we have Tarn, our junior chief technical officer and our avionics lead. We have Rehan, who's on the call today as a co-safety lead. Unfortunately, Vicky could not be with us. We have Ali, who is our structures lead, Raf, who is our payload lead, and Jan, who is our flight performance lead. So this is just a short overview of our current project. So you've already seen the open rocket file, so this is just to go over the whole project. So first I'm going to start with the testing schedule. So as I mentioned, we had a couple problems with the 4FG, so we could not complete any recovery tests, but we will be doing these on May 7th. We have completed the fuselage, bow tail, and fin rigidity tests, and these are presented here. We also have completed the battery duration and telemetry functionality tests, as you saw on the third progress report. So these are just test details, but these are also, this is all information that's available on the third progress report, so I won't go over them in detail. But to start, I'll hand it over to Tarn, who will talk about the fuselage compression test.
So in order to,
I'll stay with the mic, yeah.
So in order to test the actual realistic elastic modulus of our section to make sure also that we didn't fracture or have some unfortunate failure within our structure during flight, we created a second structured piece that is about 8 inches long that emulated the current structure of a rocket, and then subjected it to about 100,000 newtons of force, which was the max that our machine could go to. That gives us about 12.5 times factor of safety, considering we have about an maximum 8,000 Newton initial thrust. It also sustained very little deflection, which was awesome to see. Ultimately, though, it's perfectly fine for the 8,000 Newton ignition.
Right.
Then for boat tail results, there's a bit of a worry about the structural capabilities of the boat tail during analysis. However, we decided that we would test it out and make sure that it was fully capable of achieving the results that we needed without fracture, without excessive deformation. So we subjected it to under the same test procedures as the structure test, and found that it was able to sustain far higher than the expected load of 8,000 newtons, including a analysis of a amplification factor, if there was going to be one, in the sense that the ignition would actually shockwave back onto the boat tail. And we found that even in the worst case scenario of about 1.5 times amplification, there was no significant deformation in the plastic soil. When it comes to fin flutter, this is the most basic analysis that we have so far. We are planning to continue with a fin flutter analysis to see if we can get even higher results. However, right now we have at least a 3 times factor of safety, or about 2.5 times factor of safety, using a shear modulus of about 600 KSI, which is a widely accepted value for carbon fiber materials. However, we are planning to do further analysis when it comes to the shear modulus in respect to the elastic modulus. It's quite difficult to get proper readings, so we will be doing a little bit more work there, but based off the initial calculations, we're well within safety.
So this is just our flight overview. So these are all of our different simulations that we did. So we had our nominal flights, which was primarily used to compare to RAS Aero, and to make sure that the speed of supersonic speeds, the data was correct. So we cross-referenced with RAS Aero. We included here 3 different scenarios. So the first salvo flight, which is at 9 a.m., so would be minimal wind conditions. It would be the perfect nominal flight. For these simulations, we all get around 27,500 feet, which we know is not ideal. It does not reach to the target parameter of 30,000 feet, but unfortunately we had to add weight, and following the fin layup, the weight of the epoxy was heavier than we had anticipated, so our rocket is heavier than we believed. So as you can see here, at average wind speeds as well, and first salvo flight, we are stable. However, when it gets to 30 miles per hour, which is the limit that you are able to launch at, we do become not stable, so below 1.5, which is does not comply with DTEG. To counter this.
Let me interrupt there. The maximum we can launch at is 20 miles an hour under the EEE safety code. And we tighten that a little bit at spaceport. So the maximum is 18 miles per hour sustained surface winds. So you're fine.
Okay. We can correct for that then with your calculations on.
Yeah, perfect. We will adjust the flight submissions, but yeah, in that case, then we are well within the minimum stability calibers. I've also. Sorry?
What length did you use? What length did you use for the velocity off the rail calculation? What length of rail?
We used 17 feet, a 17-foot rail, but we subtracted the distance between our 2 launch lugs. So the space between our launch lugs is about 3.5 feet. So we used 13.5 feet, I believe, or 14.
Good. Okay. These look great.
Thank you. Yeah, and I've also included the drogue descent speeds and the main descent speeds, but as you know, you have them as well in the open rocket files that we had submitted. So this is just an overview of the first salvo flight. So I've included all of the launch events. And then here is a more detailed view of from takeoff to the first ejection event.
I gave you at the end of my review of your third update a list of the changes that we've made. I missed one of them, and that is that we are trying right now to have our flight hours, our waiver open at sunrise, which is 6 a.m., and close at sunset, 6 p.m.
Okay.
So the challenge at sunrise will be cloud cover, and that will be, I expect that will impact 30K flights. 10K flights will have to play it by ear. So there is a good chance that we can get your rocket off the rail earlier than 9 a.m.
Okay, perfect.
And we will be opening the gates much earlier to let students in.
Oh, I also had a question. How many chairs will you be providing per team, if you know?
I don't know, but we have from your third report the number of students that are coming.
Yeah.
So I'm not actually involved in that part of the logistics. I'll check. In fact, I'll be having lunch with the president of Ezra tomorrow. And I would expect that the logical thing to do would be to take the number of students that are coming, add 2, and use that number. But logic doesn't always prevail in these things.
Okay, good to know. We'll bring some backups just in case. I'm gonna hand it over to Tarn as well again to talk about the avionics.
So since our last report, we have since changed our flight computers since we found an issue with the Easy Mini flight computer. We've switched to a Blue Raven as our main computer with our Telemega V5.0 as our backup. This is just to allow for a bit more ease of use, which we know that the Blue Raven has a much better user interface. However, we still will be using the Telemega as our backup and as well as our GPS and flight tracker. Again, we still have our Featherweight as our backup flight tracker and just GPS reliability for recovery.
Have you guys flown the Raven yet?
We have not. However, we do have experience with the Telemega from last year.
Okay, so the Blue Raven's a very, very capable device. So make sure you have updated the firmware on it before you get to the event, and that someone is very familiar with how to use it. Also, we did encounter last year, since the Featherweight products do OTA updating, we did have a case where one component updated and the other didn't. I don't remember which. It might have been the mobile app, rendering the system unusable at the pad. So make sure you're all up to date before you start, before you want to head to the pad. And you guys will love the day you get off the Blue Raven.
So yeah, so that, I mean, it's suggested by our record, Alan, who's on the call, and he has a lot of experience with it. So we'll be regularly conferring with him to make sure that we are using it to its fullest ability as well as reliability, making sure that we have the right updates, and he will be there with us on the launch day.
Excellent.
So here I've added all the information for our avionics subsystems, but again, these are given in the report, so I'm not going to go through them. I just wanted to show them just in case. And I will be sending the presentation in a PDF format later after the meeting. So now we're just going to go over the full assembly. So specific components that we can't see because, for example, the fin layup has already been done. But as you can see in the top, we have here is our forward section. Here we have our payload, our deconstructed payload, our recovery bulkhead, and our avionics bay. We have our nose tip and our ballast, and then we have the motor casing here. We have the coupler and the aft recovery bulkhead. Here we have the fin can and the fins, and here we can see the fin slots, but as you know, this will be a lessons learned for this year. We will not be doing slots next year. It'll be inserts, as you had mentioned. We have our 4 centering rings and our boat tail here. Here is just a close-up of our fin can assembly. And we have provided details about how it was assembled, but we'll just go over them right now, just so, because it was I think in the first report, so it's been a bit of a while. So we're just going to go over the FinCAN assembly.
So it's relatively straightforward. We have about 9 steps here. Most of the internals were set up beforehand before we put it into the rocket. So that involves epoxying the centering rings to the motor casing in a way, which is a carbon fiber tube that extends into our 3D printed aft section, 3D printed out of carbon fiber. And that is something that we have put under substantial load to ensure that its reliability. We also have an aluminum T6061 aft ring to prevent any unwanted burning of material or destruction of material. The fins were then epoxied onto that, slid all the way into the slots made in the side of the fuselage. And then once those were in, there was a few drills poked in the side of the rocket to allow for epoxy to be poured into the motor can. With the fin can, this was then tilted at different angles to make sure that we got the right adhesion between the fuselage and the center rings. Finally, we did do a carbon fiber layup of the fins with a 1-inch fillet of epoxy around the edges to strengthen the root cord. This should hopefully allow for a bit more strength given the slot design that we have. So we're not too concerned about that. However, again, yes, lessons learned.
For next year. So this is just an overview of the recovery system. We currently have it packed inside the rocket. Everything fits. And I've included the harness sequence just so we can see. So our system, as you know, is a single deploy. We have 2 parachutes, our main and our drogue, 10-foot main and a 5-foot drogue. We have fire blankets and a deployment bag just to ensure that nothing gets burned because we are using black powder charges to eject the nose cone. We have 5,300-pound rated Kevlar shock cords between all of our components. And we have swivels and quick links that were ordered from McMaster-Carr and ordered at the correct rating to ensure that everything is strong.
Rated 800 pounds with a maximum force of about 10 Gs, so about 400 pounds maximum force applied to them.
Yeah. So here, as you can see, we have the aft. So when the first ejection charge goes off, the aft will pull out and then pull out the drogue. Here we will have our cable cutters who will retain the main parachute at the secondary recovery event. The cable cutters
main deploy.
Yeah, main deploy, sorry. Then when the main deploy goes off, so the cable cutters will cut here. These are all going to be connected to this swivel link to ensure that we don't have random pieces just falling out of the sky. And here the main will go with it. The deployment bag will be pulled by the drogue and ensuring that the main deploys. And it will be attached to the forward section here.
Okay, so the black line that connects from the top of the quick link to the main, that is your Kevlar shock cord going to the swivel on the main. Is that correct?
This one?
Yes.
Yes.
Okay, and the squared line is to the D-bag?
Yeah.
Okay, what is the length of the black line, that shock cord?
This one is 36 feet.
Okay, so you're good. So you've taken into account the expanded length of the main to its to the peak of its canopy and all the shock cords. To
Yes.
make sure that it gets completely out of the bag. Good job. Okay, great. Let's go on.
Perfect. And here I've added our black powder charges. As I said, we haven't tested them yet. So these are just our baseline expected and maximum charges that we can hold within the charge wells. We don't expect to go to the maximum charges. These have been calculated based on, as I mentioned, the volume, but also the maximum force, the maximum pressure, the maximum force applied to the generated by the black powder, which is 350 pounds force, which is generally the maximum force you want applied. And then here for the main deployment, the black powder charges were calculated based on the nylon properties of our
The shear.
yeah, for the cable cutters, it's what is the
shear strength.
No, the name of the type of cord we're using.
The paracord?
Yeah, the paracord, sorry. So nylon paracord.
Okay, so a couple things to take into account on this. At 30,000 feet, you start to lose effectivity of BP captured in rigid containers, which is why a lot of people at this altitude and above will use CO2. So be careful trusting your models on that. Another observation I'll make is that as the expression goes, blow it out or blow it up. Generally, your backup charges will be an additional, well, not generally. Let me open a paren. There is no single perfect answer to any question in rocketry. Everybody has different opinions, and it's up to you guys to figure it out. I will generally go an extra 50% for my backup charges. The thinking being, since I have vents in my recovery bays, right? And you have time between your primary and backup charges, you're going to bleed pressure from your first charge. If the first charge, for whatever reason, doesn't separate, firing another charge of about the same size doesn't really improve your probability of getting it apart. And the downside of that is coming in ballistic, destroys everything. So you might as well blow it up or blow it out. So a larger backup charge, particularly at a higher altitude, might be something you want to consider.
Okay.
Nothing wrong with these.
Would you suggest we put the maximum charge in for the backup charge then?
Well, in this case, you're going to ground test, right? And the ground test will give you some indication of your main deployment. But remember, we're also 4,000 feet MSL at the launch site. So you're really talking at 5,500 feet for your main and 33, 34 for your MSL for your drogue charges. So ground tests to verify your initial calculations. Well, and the cutter is a different thing because that's contained more tightly. Yeah, so if you find that 4 to 4.5 is a good charge for your primary, I wouldn't be at all hesitant to go 6.5 to 7 on your backup charge. Now, another thing you might consider, Jim Jarvis has done a lot of work on high altitude BP charges and has published some of that stuff. Now, he uses some pretty elaborate fixtures. What I have found is silicon rubber tubing. And we've done some high-speed video, and it shows that you can get much more combustion in the tube before it breaches. So the problem at higher altitude is that you tend to, the BP tends to get out into the bay from your charge canister before it can light. So you'll find a lot of unburned powder in the discharge in your E-bay, which is why it's less effective. So you need to try and contain it. Look to me like you're using kind of standard charge wells, and those will blow the powder out at these higher altitudes. So more powder, or try containing it, for example, in rubber tubing, maybe. Something to consider. I mean, you guys are experienced and you've flown before. So again, this is one of those, I do it this way. I have tested a lot of different configurations and have landed on this approach, but there is no single way to do things.
Perfect. And I did want to add these charges were calculated with the 4,000 feet of elevation, just so they're more precise than just 30,000 feet.
Good.
That was all for presentation. We have the rocket prepared in front of us if you would like us to show it.
Yes. Also, you guys, I'm sure, have thought about this, but consider that the winds that we have in New Mexico will, in all likelihood, result in pretty substantial horizontal velocity at apogee, your first deployment event. And you'll need to, just to give you an example, I had a team last year that was attempting to deploy from a hatch on their nose cone, spring loaded. Well, they were doing about 250 feet per second horizontally, and the aerodynamic pressure, the best we can figure out, kept that hatch from opening. And if you're doing 250 feet at apogee, it's not going to get any slower as you head to the ground. So they never deployed anything. And they also never found anything. So it's buried somewhere in New Mexico. So you know, take into account the fact that you're going to have some pretty high pressures at apogee.
We have our current flight performance lead is working on some wind simulations to ensure that it's part of our go no go checklist. So if the winds at 30,000 feet are too high, we will not be flying because again, it would just be dangerous. So we are currently working on precise wind simulations. So I'll stop sharing my screen and I'll make yours the spotlight. Perfect.
All right, what do you want to go over first?
We can start. Yeah, we can start with the avionics.
All right. So we have a. We have a 3D printed avionics bay just for ease of mounting and circuitry to make sure that we can see all the connections and ensure proper connection between each point. On one side, we have our main avionics system, along with a featherweight, which will be installed above this with its antenna. This is connected up to switches at the top. Unfortunately, we had a few issues with securing some switches, but they will hopefully arrive today. So we'll be able to slot that into the avionics tomorrow. Both have been tested, however, with the same set of switches, and will be tested again once we have the full setup basically set up. We have the LiPo charges set behind this panel here. We'll have two on this side, along with one on this side. The one on this side will be going to our secondary auxiliary computer, which is our Telemega V5.0. Same situation, we have our switches up top, and on the past report that was sent, we have the circuitry images for both the Telemega and the Blue Raven chargers, computers. These are then routed through the, pardon?
Just a suggestion, the blue capacitor on the Blue Raven, that's used to ride through power outages. The next time you're mixing epoxy, you might want to put a dot underneath that to hold it in place.
Okay.
So these things, if you get a lot of lateral motion, you're carrying that load on the leads.
Yeah.
So I tend to epoxy those down on mine.
Awesome. Thank you. That's a great suggestion. Then we have them just routed into these blocks for transfer to the igniter charges, and then that will be transferring down our service module into our explosive wells, along with our shoe cutters.
And the batteries you're using, you got from Featherweight for the tracker and the Blue Raven.
Yes, they both came with the package of the Blue Raven.
Okay, and what about Telemega?
The Telemega will be reusing the ones from the last launch, which also came from manufacturer.
They came from
Telemega.
I didn't think they sold batteries.
When you purchase the where we got it from, when you purchase the Telemega, this in and it does say on the website, I believe, that it's suggested by the manufacturer. And we have flown with it before.
Well, we changed the rule from last year.
Yeah. If need be, we also received a LiPo in the ground station for the Blue Raven, which would be certified for flight and could be installed in the Telemega. Yep.
No, it's not. It's not the same manufacturer.
Not the same manufacturer.
Okay.
It would have to be 9-volt batteries.
Okay. We can make that work.
Well, or 16, 18650s would probably be a better one. So let me give you a little bit of background on this. We had 2 LiPo fires last year in rockets, along with exposure of a couple of students to the chemicals inside failed LiPos. That's fundamentally the reason, that's the first reason that we're not allowing them. The second reason is that we have seen a propensity for teams to use very large LiPos. So you could do, say, a 5,500 milliamp hour 1S, and with a 60C, for example, discharge rating, which means that that thing could pop enough current to blow the output stage on many altimeters, probably all of them if they're not properly protected for overcurrent. So the approach we've taken is we're making an assumption that if a manufacturer supplies a battery, that the manufacturer has tested that battery with their device, and thus are able to say, yes, we have test data that shows that this battery will work with our flight computer. Unfortunately, I think, I'm trying to find it, I think the Altus Metrum website gives you a voltage range, but not a current limit. And I just can't find it right, because I went through this with Mississippi State Saturday, and in which case we don't know that Altus has tested with a specific battery. So switching to a 9-volt or an 18650 would be compliant with the rules, but using a LiPo, since you can't buy them from Vidale's website, then using a different LiPo is not going to work for the Telemega.
Okay.
Also, I went through this with no one's flying it, but the Kate system, or actually the AIM Extra system, they're out of South Africa. So in my conversations with the Entrecore guys, to me, it's unreasonable for me to require them to import batteries to South Africa to test and export to the US. So what we've come up with is that they are now publishing on their website, we have tested with these batteries, these specific specifications of batteries. And that way, those batteries can be acquired from another source. I don't have that right now from Altus. So you need to look at using a different, not a flat pack LiPo. I would suggest an 18650. They're easy to get, and just the run of the mill ones can provide 10 amps continuous. And if you need more than that, you can do 2 of them in parallel. And those are metal can lithium ion batteries. So those are safer than the LiPos, the flat pack LiPos.
Okay.
I just don't want you guys to run into an issue during our safety review at Spaceport.
Yeah. We'll probably be purchasing 186050s then. 18650s, sorry.
Okay. That looks good.
Continuing on to structure. Unfortunately, we cannot open the fin can since that is all secured together now.
So do you guys do you have vents in the recovery bay?
Yes, we will be
Yeah.
we will have vent holes, but we haven't drilled them yet.
Okay. Fine.
Currently, the holes we have so far are for our main pins at the moment, which will serve as minor vent holes, but we will be allowing for flow throughout the service module as well.
Okay.
And
So how many of you were at Spaceport last year?
3 of us are still in the 2-hour at Spaceport last year.
yeah.
Okay, so you guys are familiar with how bright the sun is out there.
Yep.
So consider that in terms of being able to get your arming, disarming pins in the rocket. I'm thinking particularly recovery, because you'll be inserting them before flight under cover, under shade. But out in the field after recovery, that can be a challenge.
We have come up with a solution with that because that was a problem raised. We would be 3D printing some jigs to stick onto the avionics bay. We're also going to be making our holes smaller because they're oversized. But we'll be making a little, like a kind of like a little funnel. That way it guides the pin into the hole.
Perfect. Good thinking.
And yeah, so we can go ahead and open the rocket just to show the parachutes and everything that's been packed in.
By the way, it looks great.
Thank you. So we have our coupler here, and then when we go inside, we have first, this is the bulkhead that will obviously be attached to the coupler. We have our
That's the motor cave.
the motor cage, sorry. Our drogue and our main, and we'll be adding some fire blankets. Considering we're using a lot of black powder, we've purchased extra fire blankets to protect any lines and the parachute here.
So are those quick links? Those look like 1/4 inch to me, or are they larger?
They're 5/16.
Okay.
No, they're 3/8. Sorry, they're 3/8.
Okay, so that means they're about 2,400 pounds braking force.
I believe so. But on McMaster's website, that's what they're rated for, but they say that they have a safety factor of 5.
Yeah, so
Looks good.
the actually this quick link was not this was not attached, but obviously it will be during flight. So here we can see our charge wells. And then when you pull out, you have the payload, so our service module. Here we have a decoy avionics just for the presentation. We have our steel rod secured with bolts here, and this is connected, and the ballast will be put here, and this is securely tightened in with the nose cone.
That's a 1/2-inch steel rod.
Yep, very good.
And Yeah, so I think that's it for our presentation. I don't know if you wanted to see something more in detail or had any questions.
Let's see, what are you using for shear pins?
We're using 5 40-pound nylon rivet shear pins. They're rivets that can lock into the rocket.
Okay. What is your payload?
Our payload is radiation sensing, so it's our payload. It's not assembled in the video. It's still the avionics section is being worked on. But what it is, it's a cloud chamber, like to measure ionizing radiation, and we also have an actual Geiger counter inside the payload, so that as the rocket ascends, we can both visually see with a camera in the cloud chamber more ionizing radiation as we ascend higher up into the atmosphere, and then compare that to the Geiger counter's readings and see if there's we can see a visual rise in radiation with a working cloud chamber. So it is actually cooled by a 1-pound block of dry ice in the payload bay.
And we've oversized the dry ice to ensure that it will survive long enough on the pad or in the desert.
Despite the heat.
Yeah.
Well, we will, well, as I tried to show in the list of things that we've changed, rockets won't be sitting in the sun.
Yeah.
Students won't be sitting in the sun. So hopefully we won't have to worry too much about cooking.
And
I'm sorry, go ahead.
Just back to the shear pins to finish up there. These are the shear pins that we have. Just nylon basic rivets. 40-pound strength.
Okay.
And the strength has been calculated based on the drag separation force on the rocket. And there's a safety factor of 1.9.
Okay. How are you doing motor retention?
So in here we have a snap ring, just a C shape for basic motor retention.
Okay, that piece is made of can you pull it out for me?
Yeah. Here's
Where are your glasses?
Can you guys put safety glasses on, please? Oh, I am.
Thank you.
Okay, bonus points to whoever pointed that out.
So team
And then
lead.
a leather glove on the opposite hand really helps when they slip.
Let me.
Oh, damn it.
Yeah. You. Thank you.
Okay, got it. And then you're tying your shock cord to, or you're attaching it to an eye bolt into
So it's the top of the motor, the motor cap is directly attached to one end of the recovery system.
Yep. Okay. Let's look at the rail buttons.
We actually haven't put the rail buttons in yet. We are going to put them in after we paint. We do have them here. They're over here.
They're standard 15-15.
They're 15-15 purchased. They're Delrin.
Okay. That's all I need to know. How are you attaching them?
They're being riveted in with 1/4-inch Marson aerospace rivets.
And we'll be putting in
Yeah.
blue Loctite.
I don't think Loctite is going to help the rivet.
A 1/4-inch rivet.
1/4-inch aluminum rivet.
Okay, and you've checked those on a section of 1515 rail.
Yep.
Actually,
All right.
We used the same ones last year with no issue.
Okay, all right, good.
we have
Let's see.
we have a piece of rail just in case so we can test it.
Okay. Are you guys going to ship your stuff?
No.
So
We'll
you're
be
going to drive
carrying
it and you're going to
Yeah.
pick up the motor in Las Cruces in New Mexico?
Yeah. Well, we ordered.
Can't hear you, Olivia. You're mute. Can you try again? Can't hear you.
Yeah, we got. Sorry. We're grabbing our motor from Wildman Rocketry at the Hilton Garden Inn.
Okay. Yeah, Tim Lear's, he's quite reliable. So if he's got your motor for you, you're good.
Yeah,
Yeah, and we've ordered the dual sided igniter.
it's the spaceport dual-headed igniters.
Yeah, igniters are a challenge. We've done a whole bunch of testing on the system out there. But you'll get good ones. And if you don't, if we have any issues, we've got backups. So you need your team number and the frequencies on your payloads, as that's DTAG 9.5.
Our payload
Just
doesn't
sharp.
transmit a frequency.
Okay, good. Don't need to worry about that. Then you'll need them on the rocket outside. As specified in the DTAG. Obviously, we can't check it because you haven't finished the painting on the rocket.
Yeah,
Let's
I'm finalizing painting details this weekend with our sponsor, so I can have the full render ready and I can send it over to you if you'd like.
Not necessary. Don't worry about it. Let's see a few other things. If between Las Cruces and Spaceport, there is a Border Patrol checkpoint. Since you're coming from Canada and you're Canadian citizens, make sure you have ID with you.
Yes.
Let's see. Tents and tables are provided, chairs aren't. I just found a note to that. Sorry about that.
Okay.
So you'll need chairs. Do you already have housing set up?
You're mute again.
You're muted again.
All right. Let me just, can you hear us again?
Yes.
Okay. And you're the team members that are going to go out to the pad and recover are TRA members, right?
Yes. Everyone is a Triple E member, yes.
Okay, well then I'm going to go off script a little bit and say, exercise your right to vote in the Triple E elections. I'm running for the board. I would appreciate your consideration. Let's see. And you have, so you're running 433 megahertz. So you need somebody with a ham license.
Yes.
We have one.
Pierce has his.
Excellent. And your flyer of record is going to be there at the event. Excellent. I have nothing else. I think you're in great shape.
Perfect. Thank you.
Yeah, I look forward to seeing that fly. That size rocket on that motor will be really, that'll be an impressive flight.
Very excited too.
Based on what I'm seeing, I expect a successful flight all the way around.
Thank you.
So do you have any questions for me?
I do not.
Don't
Do
think so.
you- No, I think we're all good.
This is your chance. But you can email me anytime.
We have the Da Vinci stuff figured out.
Oh yeah, we did have a question about the Da Vinci. I saw in the forums that they were supposed to reach out, but I just wanted to see if you had like a time frame of when they would reach out to us to register.
Let's see. Have you submitted the form that's online? There is a form someplace. This is about, well, they'll probably start mid-May. Is my guess. I haven't talked to Chris Harris runs that whole group. I haven't talked to Chris in a while, so I don't know an exact timeline. But that he'll start coordinating all the frequencies as we run up to the event. So mid-May, that's about a month out from the event.
Our main concern with that is that we do have to be pasting that on the side of our rocket for the launch, and we would like to get our paint job done relatively soon.
Worst case, we can just write it on top.
True. We could write it.
Yeah. In fact, I would suggest you not paint anything for the frequency on the side of your rocket, because that could very likely change up to the day of the launch based on all sorts of factors at the event. Just make sure your team number is on the side of the rocket. And then, you know, as you go through final safety, you know, put the frequencies you've been assigned on with masking tape, take it off before we launch.
Okay, so we can just bring some stickers or something.
Yeah, don't hold up a paint job for that, and then because you'll just be writing over it, I expect. You know, we've got at this point we still have 138 teams coming as of the third progress report, and that's up 20 teams from last year, 21 teams from last year so far. There'll still be a little bit more. I expect a little more attrition. But it's going to be a lot of teams, which means a lot of transmitters. So that, and we can't predict when teams will want to fly. So there's going to be some fluidity in that as we, you know, work it out on the day of the launch. The day you launch. I mean, we've got 3.5 days of launch, but we can expect the hybrids and the 2-stage to be at the end of the week. They're always slow. We are, since you're going to 30K, I also have the option to put you guys at launching from the longer rails at the 2-stage pads. So we'll have, I expect we're going to have 3 pads out there, and the rails are 21 feet, and the new one will be 20, I think it's 23 feet, maybe 24 feet. But of course, you can stop it up the rail to get whatever you want for rail distance to the top.
Well,
You guys, it's clear that you guys have put a lot of hard work and thought into this project. It looks really good.
very much.
All right.
I haven't seen the form for the Da Vinci thing. Would it be on the IREC website or the HeroX?
Well, we try and put things in both places. So if you haven't found it, that means they probably haven't finalized it.
Okay,
Cool.
perfect.
All right. I think that's it.
We look forward to meeting you at Spaceport. Thank you so much for the meeting and for the suggestions. And yeah.
Thank you.
Thank you.
All right. I'll see you in about 5 weeks.
Yep.
5 weeks?
Yeah.
Is it?
6 weeks.
All right.
Yeah.
Next
6 weeks. All right. Well, thank you very much. I appreciate the time. And you've been recording this. So please send a link into Ezra. And then I think, in fact, the instructions for that might have been. Yeah. I thought that they might have been on that rubric I sent. I've seen them someplace published. And then we'll go from there.
Perfect.
Again, thank you very much for your time. Good job.
You as well.
And, relax between now and the event.
We got next year's rock to think about.
All right. Good night.
Good night.
Good night.
You.